Okay. So, Gaussians. Well, I guess everybody has seen a normal distribution before. And if not, at least if you grew up in Germany, you would have paid with this up to about maybe 15, 20 years ago, basically before the euro. And yeah, Gauss was German, and Carl Friedrich Gauss. And here's one of his most famous contributions, namely the Gaussian distribution, sometimes also called the normal one, including the equation, which kind of made exam questions along the lines of write out the Gaussian distribution kind of pointless in Germany for a while, because you would just take out your 10 Deutsche Mark bill and you read it off if you had to. Well, joking aside, I mean, people still failed that, yeah, unfortunately. But yeah, here are some examples of the normal distribution. And as you can see, well, large variance just means that they are fat. And small variance means that they're narrow. And if I shift the mean, well, then you can see that they just shift. Okay, well, I guess we all know this. And we've actually done that kind of stuff in the exponential families context. But we're going to look at Gaussians in a little bit more detail now, because we will actually need this as we go along to deal with things like Gaussian processes. Gaussian processes are something that you effectively already calculated in homework 1 or homework 3 when you looked at a linear model with additive noise. And then at some point you needed to look at computing the covariance function. And that's pretty much what happened. So that homework was there for a reason, namely to unscare you or maybe permanently scar you for Gaussian processes. So Gaussians in space look exactly the same thing, except that now, of course, we have, in this case, 2 dimensions. And so what you see underneath, if you can squint really, really hard, is here you see, well, the equipotential lines, and I'm nowhere near as good as MATLAB. And then up here, it's basically the, well, contour plot. Well, the basically the surface plot. Okay, now that's all fine. An interesting thing in this context is these Gaussians are characterized by their covariance, and they have principal axes, right? And those principal axes are actually orthogonal to each other because, well, you have a positive semi-definite matrix, so you can get all the eigenvector-eigenvalue pairs, and we all know that the eigenvectors are orthogonal to each other. This is actually also one of the reasons that if you take a spinning top, there are going to be 3 axes of rotation for the rotational tensor, and so you can always spin a spinning top. You'll always find something where it doesn't it isn't out of balance. Okay. Now, here's some samples drawn from that very same Gaussian, and it just looks as you would expect, namely where you have more density, you draw more samples, and out here where you have very little, you draw very few samples. Of course, the desirable thing is to go back from some gray mush like this to these very pretty black vectors. Well, now they are green, but they were black before. And then to infer, therefore, what the principal directions are, and also what their length is, and because that corresponds then to a covariance matrix, right? So if you don't recall that, we have basically sigma equals some I equals 1 to D, lambda I, vi transposed. And yeah, sorry, sigma and sum are the same Greek symbol. In LaTeX, you could distinguish it. On an iPad, you can't. So let's look at this in a little bit more math. And this is exactly what you would expect. So for a scalar variable, well, you have a mean, mu. And you have x minus mu, and you can see exactly that this thing is maximized for x equals mu. And then you have here you divide by the variance, right? So sigma squared. So a slight the tricky thing, at least you need to be mindful of that, is that if I have d dimensions, then since I can have essentially a Gaussian in arbitrary directions, I need an entire matrix. And people usually don't write sigma squared anymore, but just capital sigma inverse. Yes? That's exactly what I'm talking about right now, namely that, yes, here. Yes, it does. Sorry. Okay, yes, it's missing a square. Let's pick. Thank you. Yeah, good catch. But here there is no square. So compare this. So basically, bear in mind that usually if I have just sigma, I talk about the standard deviation, STD. And if I have sigma squared, I talk about the variance. Just when you write things out and you want to explain things to other people, make sure you distinguish between those two things in terminology, otherwise you'll confuse the heck out of them. And now here the sigma is a covariance matrix because it basically measures not just how much those variables change, but it also measures how much they change relative to each other. And we'll get into analyzing this in a little bit more detail in a few slides from now. So the first thing you can do is you can just ask, well, if I have a positive semi-definite matrix, or in general a symmetric matrix, I can just throw linear algebra at it. And so the first thing you would do is you would ask, what are its eigenvectors and its eigenvalues? And so I can just write out sigma is u transpose lambda u, and we know that u are all, the matrices u are rotations, right? And so all this does is it basically just takes x and it shifts it and it rotates it. So if you think about it, it takes my vector x and it picks a new offset, let's say here, and then it goes and rotates this in order to maybe get something like this. Okay. Now, what happens then is this new vector, let's call it maybe z. Okay, z transposed lambda inverse z. Well, that of course decomposes now into sum of a zi squared divided by lambda I. And so now this is basically a normal distribution in each of those zi's separately, which are then rotated in order to get and shifted in order to get back to the original result. Or furthermore, I could actually take the square root of lambda and get something as follows. Let me quickly write this out in detail. Okay. So let's start with e to the minus 1/2 x minus mu transposed sigma inverse x minus mu. And then, what?
It's good now. The lighting.
There's what? Sorry, I cannot hear you even here.
Lighting was off.
Okay, the lighting is well. Okay, I can. Let's try this lighting. That should be better. Okay, good. So, and of course I have the upfront factor here of times, 1 over 2 pi to the d over 2. And then I also have the scaling, which is basically 1 over determinant of this matrix. Okay? So now, let me see whether I can change the contrast. It actually has a button here somewhere, but okay, fine. I hope it's okay. So what happens is that you can actually now rewrite this appropriately. And the way how I'm going to rewrite it is as z equals sigma to the minus 1/2 x minus mu. Okay? So if I do that, I do get that the exponential term here now becomes e to the minus 1/2 z transpose z, which is nothing else than the product I going from 1 to d e to the minus 1/2 zi squared. Okay? And yep, okay. So now this looks exactly like individual normal distribution zi, which I then take and apply this to get x back, right? So I can actually solve this system of equations. And I get that x equals sigma to the 1/2 z plus mu. Okay. So this is actually how you go and generate Gaussian random variables that are colored Gaussians, as in that are not white noise. You basically start out by invoking your favorite Gaussian random number generator. And once you've invoked that, you then go and, basically you multiply it by the square root of the covariance matrix, and then you shift it. Because these were zero mean, so linear transformation. So scaling doesn't change the mean in this case, because it's zero mean. And then I just shift it. Okay. Does somebody have an idea how I can take the square root of the covariance matrix? Okay? Exactly. That's the right way to do. That's the one and the only and the right way to do it. And the good thing, so let me write out the name. And in MATLAB, I think it's called col. And furthermore, if you are using BLAS, it's called something like SPOTRF. Single or alternatively double precision, positive, semi-definite, triangular factorization. That's where the name comes from. This is object-oriented programming in Fortran 1970s style. Because they had a length limit on the function calls, about 6 or 7 characters, and they wanted to essentially have an object-oriented program API, right? And that's very hard in Fortran 77. So what they did is they basically put parts of which object it applies to, what it does, into the name of the function calls. So you get something like, you may have seen that if you go to a gaming website and they benchmark the latest GPU or CPU, and then at some point they will talk about, well, now let's do a compute benchmark, and then you will see something like dgem. Double, general, matrix, multiply. Matrix, matrix, multiply. Yeah. So thanks goodness by now you don't have to remember all of this bizarre stuff. There's something a lot less hostile. It's called Eigen. And if you're doing linear algebra in C++, you will be very happy if you use this instead. Okay. And I can ensure you that a lot of big companies use eigensomewhere, and yeah, they don't do this anymore. This makes it a lot harder to write horrible code. Okay. You can still write horrible code, but you actually have to try. Okay. Okay, good. So, well, actually, there wasn't really much of a reason why we should even go through this, right? Because we already did the exponential family anyway. So this was just one of the lines of the distribution that we encountered in the exponential family, right? Okay. So all I've done is I've just gone into this in excruciating detail, and what we saw is that, well, looking at a normal distribution, has its benefits in terms of modeling things in terms of mean and covariance. And yeah, I mean, basically fitting the parameters is, you just will go and compute your empirical mean, your empirical variance, and then you just fit it. Okay, at least if you just do a maximum posteriori, maximum likelihood fit. Map is a little bit harder. Let's have a look at this in pictures again. This is exactly, well, you have your principal components, and the connection between ellipsoids and matrices, I think, should be fairly clear. It's basically the equipotential lines here in the quadratic form x minus mu transposed sigma inverse x minus mu. And that's really all that there is. Okay. Any questions so far on the math? Because we're going to use it a little bit. Okay. Everybody cool with normal distributions? Because we'll use them a lot for the rest of this class. Okay. So the obvious thing is, why do we care? Well, the first thing is it's really trivial to estimate the parameters. As in, everybody would have probably done this at some point before. You just take the average, and in order to then estimate, let's say, the covariance matrix, it's also very, very easy, because all you do is you just take second order moment, and you subtract the mean from it that you just estimated. So actually I should put a little hat on this. Yeah. And then that's it. If you at some point take an information theory class, you'll see that exponential families distributions are those distributions with the largest entropy. Right? And, well, basically with the largest entropy subject to a constraint in terms of their moments. For a normal distribution, so for a Gaussian, that's constraints on the first and second order moment. So among all distributions that have a given mean and have a given variance, the Gaussian distribution is the one with the largest amount of uncertainty. It's the least committal distribution under those constraints. That's why Gaussian distribution is actually quite popular when you're estimating things, because if you only have, let's say, the first and second order moment, and you want to, deal with even fairly unpleasant cases, then, well, a Gaussian is often not going to be a bad fit. The other reason why a Gaussian is, of course, nice is because, as we saw, if we add enough independent random numbers together, we will get conversions to a Gaussian, right? That was Bayes' central limit theorem, where we looked at that and we looked at the rates and we established all of this. Right? It was maybe about a month and a half ago. The other thing is, for all of those reasons, this even works really well, even if the assumptions are mildly wrong. So if you have no better idea of what to do, starting with a Gaussian is never a bad idea. This entire thing is trivial to do in MATLAB, right? Or in Python, or whatever. So in 2 lines here, I've estimated the parameters of a Gaussian. So X was basically just one giant matrix where row by row you had, the entries, basically different observations, and there you go. This will give you, mean and covariance. Okay, so this is about as simple as it gets, and yeah, a high school kid can code this up. Any questions about it so far? Okay, let's move on then. Sampling from a Gaussian, the first part, we already saw that, right? So we already saw that basically if we want to sample from a colored Gaussian, so with mean mu and covariance matrix sigma, then all we do is we just factorize sigma, and we basically perform this. So that's what you would do in pretty much any modern programming language. They would have probably some primitives for drawing from a normal distribution, or at least they would have some library which does this. Even C++ has it by now. And then you just rescale. And of course, proving it is fairly straightforward. You just plug in the means and that's it. Now, the question, however, is, where on earth did our Gaussians come from, right? So, somebody must have invoked a random number generator at some point. How do we get those Gaussians? Because drawing from a uniform distribution is fairly easy. So we know that with number theory and so on, you can do something there. But drawing from a Gaussian, well, looks kind of hard, especially given that the integral is, non-trivial to compute. So if I have, if I have this integral to compute, and I need to then, basically do the inverse transform for the probability integral transform. So basically I look at the cumulative distribution function and I have to invert it. Well, that is hard, as in there's no closed form solution for that. So the question is, how can you do this efficiently without excessive access to tables? And the trick is actually amazingly elegant. So the trick is basically you go to 2 dimensions. This is also called the box-Muller transform. So what you do is you basically, let's say we take x1 and x2, so we have, some vector x. So I know that if I have, a normal distribution in 2 random variables, namely x1 and x2, okay, so I can maybe draw from both of them at once more cheaply. And, with unit variance, this is basically the density that I'm getting, right? Now I can go and transform this into polar coordinates. So basically into a radial part and a spherical part. Since this entire thing was rotationally invariant before, I immediately can see that I have a uniform distribution over the angles. So the angles are between 0 and 2 pi uniformly distributed. So I can easily draw from that. That's just a sample rand uniform, and then I multiplied with 2 pi, and I got the angle. So that's trivial. Now, the radial part, I actually need to do the following thing, and I kind of forgot about that here. I need to actually have a radial part, namely, essentially, times 2 pi r. This is actually how the 2 pi can easily be calculated and how they cancel out, right? Because now the radial part, I basically need to go around this entire segment, and that's of course 2 pi r. Okay, it's just variable transformation. Okay, and so now I can easily solve that integral, and I can see that the cumulative distribution function in phi and r is now phi over 2 pi, and then it's just 1 minus e to the minus 1/2 r squared. And that I can invert. So I can basically take care of this first part separately. That's trivial. And for this, I can actually solve the equation. Okay, let's do that. Right? So we have, let's say, z equals 1 minus e to the minus 1/2 r squared. The reason why I could solve this integral is, of course, because I had the integral of r times e to the minus 1/2 r squared, and its same function is just e to the minus 1/2 r squared. Right? So if I have to solve for z, well, from this it follows that I basically have 1 minus z is e to the minus 1/2 r squared. Actually, 1 minus z is also uniformly distributed if z was, so I can just flip things, right? And then I need to solve for this part in the equation. So I basically get, let's just call this thing here v, because it's, again, uniformly distributed. So I just have log v. And then I will get a minus 2 and a square root. And this will give me the radial part. And so now, once I have the radial part and have the angle, I just need to use sine and cosine to get everything else. So basically, I pay the price of 4 complex functions, namely logarithm, square root, sine, and cosine, to get this, in addition to 2 uniform random number generators. And that's what gets me to Gaussians. There's a couple of other transforms, but this is actually one of the most intuitive ones. Okay. Now here's a last trick. If you have to draw a lot of Gaussians, and with a lot I mean like many, many millions or billions, right? So even though this transformation here looks okay, it can actually become expensive fairly quickly. So how do you engineer around that? Well, one thing that you can do is you can just go and draw maybe 1 million Gaussians, samples from the normal distribution, maybe 100,000 beforehand. And then after that, each time you need to draw from a Gaussian, you just pick a random entry from there. And you can actually prove that this is essentially indistinguishable from a Gaussian as long as you don't draw more than, a quadratic order of those terms. So in other words, for all practical purposes, this is good enough. That can speed up your code a lot because a K-Schmiss is still cheaper than those 2 or 4 higher order functions to be invoked.
I'm sorry.
Yes?
What did you do? How did you generate the table?
Well, I go and generate the table once, and I just draw from a Gaussian maybe 1 million times. So I basically create a supply of 1 million Gaussians. So maybe let's make it 128,000 Gaussians, right, in double precision. So this uses a megabyte. And then I just set that 1 megabyte location aside. And each time I want to draw from a Gaussian, I just look something up there at a random location. So you care about that if you want to have very, very high performance code which needs a lot of Gaussians. Otherwise, you don't care. If you need a couple of them, if it's not the key factor, okay, don't worry. But if you need a lot of them, this is really something you should actually take into account. Okay. So here's the MATLAB, Python, or whatever code. They all look pretty much the same. There you go. This is not high end. Yeah, we talked about that. So now, the next question then is, does it actually mean something if I take some observations and I just project them onto those what are called principal components? So the principal components are basically the directions of largest variance. And yes, of course, it does something. So this is the infamous iris data set. I think it's over a century old. So at that time, this was big data. So 100, 200 observations, if you have to do that by hand, is actually really painful. And I think Fisher did this. So he is a pretty good statistician, and he didn't mind getting his hands dirty. In that case, probably quite literally with the ink, because they would use, of course, ink quills or fountain pens or something. So basically, this guy was doing applied big data analysis by looking at, hundreds of measurements of irises. But now you can do that on your cell phone in fractions of a second. And basically what they did is they plotted the first two principal directions. The lines that you see here, like sepal width and sepal length and petal length, and I'm not a I don't know botanology quite that well to actually, or I'm not a botanist, so I wouldn't quite know this quite so well what the sepal width and sepal length is, but I guess it means something for irises. And what we can clearly see is that, there are some groups of irises that are different. So there's like one species, it's the iris setosa, which kind of looks really different. And then there are, if you were to squint hard, there's like the versicolor and there's the virginica, and they sort of kind of group into separate groups as well. Right. And so this is one of the first empirical confirmations that principal components are kind of useful. Mind you, he basically ran a eigenvector, eigenvalue decomposition on paper and pen. Right. Well, it's only a 3x3 matrix, so it can be done, but it's unpleasant. Okay. Now, we still have this problem nowadays, but it might actually be a little bit, a bigger deal. So this is a slide that I shamelessly stole from Barnabas Pochos. So let's say I have, like 65 people, and I have, 53 blood and urine samples because, well, I want to measure something about them. And this is kind of awkward to see what the correlation between the features is here, right? So the obvious question is, can I actually go and measure this in a meaningful way? And so what I could do is I could just, for each of those measurements, plot the curves for each person, but that's, really awkward because you still don't really see much of what's going on. All you see is that, well, maybe you have some values where some measurements where the values change a lot and some where they change very little, but the ordering of those measurements means absolutely nothing. Then I could go and, squint at each plot per person, and that's unpleasant. And, well, what I could do is I could, plot, 2 3-dimensional visualizations, and even with 3 dimensions, that's kind of hard because, well, what is really going on with the C triglycerides and the CLDH and the MEPL, God knows what they are. But okay, the point is we need something a little bit less dumb than what we just did. And so the obvious thing is, well, is there a better representation than the coordinate axis, and do we really need to show 53 dimensions? And of course not, because otherwise I wouldn't be talking about PCA. So what you basically do is you look at the maximum directions of variation. And those are exactly the principal axis. And then, well, you can just show that, well, this gives you the smallest subspace. And yeah, okay, well, we can go through the algebra here, and I guess you all have at some point looked at the fact that if I have a matrix and I want to approximate it by a low-ranked matrix, this will make me pick the largest eigenvalues or singular values. And so that same thing happens here as well. So here's some 2D data set, and here's the first principal axis. There's the second one. Now, this is all pretty boring with that, and it's also still very boring with 53 LDH and whatever measurements, but here's a fun one. So this is sometimes known as eigenfaces. So if you do a Google search on eigenfaces, you'll probably see hundreds of papers. And the really cool thing about it was the name, because PCA had been around before faces as well. And what they did is they just said, well, let's take a lot of faces of people. And each of those faces was actually in different poses, whether they were smiling or frowning or with glasses or with a bad haircut. And then they basically looked at, what are the principal directions of variation. And so on the first picture, well, you can clearly see it has something to do maybe with the skin tone. The second one may be hair color. Third one may be whether you're bald or not, right? So if you look at that, right? Then there's a bit of lighting, namely here versus there, right? Same thing over there. And then I guess at some point it just becomes less and less obvious. So for instance, here you can clearly see this is all about whether that person's wearing glasses. Here's probably whether they're smiling, whether they have a beard, and so on. I mean, at some point it gets kind of a little bit harder to interpret, but you can clearly see that those principal directions, which in this case are, images again, because I have a space that is number of pixels by number of basically number of images. So each direction is, of course, again, in the pixel space, and so I can visualize it. But this gives you sort of a meaningful idea of what those principal components would do. Okay. Now, if you do that and you apply it to somebody's face, you can see that in the first principal component we get a human, right? And as we start adding more and more directions, it looks more and more like the guy who we actually wanted to approximate. Right. So up here is sort of the generic human, and you've probably all seen here's the average face of country X, Y, and Z. This gets published every 5 years with different data. And this is basically the average face, and plus maybe a projection in the first principal component. And you can do that, and people like to look at that. I've picked this example not because it's insanely useful, but because it's very visually appealing for you to get a feel of what principal components do. Okay, what happens if you feed in garbage, right? So these two are different people, and okay, you can argue whether the reconstruction in these two cases, it probably sort of kind of works out okay. Well, you can easily, you can figure out for yourself whether you think that Homer Simpson really has that as a human equivalent, or whether he looks like a rat or a nice convertible. But basically, what this clearly shows you is that if you pick this particular space of encoding, if you observe something that doesn't fit it, it'll make it fit whether it wants or not. Okay. The good thing is that in doing so, you will actually see a monstrous residual in those three cases, right? So basically, x minus px, this will be large. And so you can actually immediately see that you can use this normal distribution, despite the fact that people are definitely not normal. You can use it to, detect novel and unusual images. Because basically what we've done is we've done a very, very poor job at density estimation on images. And at least it'll allow me to weed out the Homer Simpsons and the rats and the cars from humans. Okay. So now the obvious thing is, well, okay, this is all very pretty. Can we do something useful with it? And this is going to get us into a little bit more math. So please pay attention to the math that follows now, because once you understand that, all of the Gaussian process reasoning is super easy. So let's start with something not very scary. And by the way, this picture here is basically a normal distribution and conditioned on a particular value on the y-axis, what's the density on the x-axis. So it's basically just taking this normal distribution and slicing it and plotting the values of the slices. Right? Okay, so what does it correspond to? So let's say this is maybe somewhere in Europe where we measure height in centimeters and weight in kilograms. And I don't know whether that's a particularly healthy distribution, but okay, you could generally assume that if you're taller, you weigh more, and also generally if you weigh more, you're more likely to be tall. So, and I'm making this horrible assumption that there's a Gaussian correlation, which is probably not true, but for the purpose of this, I can do this. And so I could just ask something like, well, maybe, given somebody's height, can I get the distribution over the weight? Right? Which, is a joint distribution, and so this is not very hard. I can just go and, compute P of weight given height. It's just, by base rule, P of height and weight divided by P of height. And this is also proportional to P of height and weight if I just keep the height fixed. And then I just need to renormalize. Right? This is base rule. We did this in the first week. Okay. Now, that's what it looks like in algebra. So I have x1 and x2. And it's exactly the same thing as what we had before. I just dropped the normalization because we have to recompute it anyway, so no reason to be particularly fussed about it. x1 minus mu1, this, and here we have those matrices. The only thing that I did is I assumed that these can be arbitrary matrices rather than just scalars. So rather than height and weight, I might have an entire set of, might have one vector that I'm now going to call height, and one that I'm going to call weight, or just x1 and x2. And so now, what I can do is so if you squint at this hard enough, you see that this entire expression is going to be a quadratic form in x2 with some parameters that depend on x1 and mu1 and mu2 and all of this, right? So what I can do now is I can just go and collect the linear and quadratic terms in x2 and use this to then figure out what my normalization is and what the mean and all that is. So just by looking at this without really doing any linear algebra, you can see that x2 given x1 has to be a Gaussian in its own right. Because only linear and quadratic terms and the obvious constant offset occur, so therefore it has to be a Gaussian. So here's what you get. I'm just going to call it t and t prime because it's a bit easier to write out. And what you do is you basically just look up a book on linear algebra. There's, for instance, one called by Lütke-Pohl, or otherwise you go and solve this once on your own. You'll want to do that once in your life. And you just work out what the explicit inverse of a 2 by 2 matrix is. That's all you need. And so here's what you get. You get that the block pertaining to t prime becomes kt prime t prime minus the covariance between t and t prime, the inverse covariance in t, and then the covariance between t and t prime. And furthermore, for the linear term, you get, after you correct for that, you get that. You get basically the original mean plus the covariance between t and t prime. And then here's the deviation from the mean between t and mu and its variance. So this is really just working out the above equation in detail. I can only strongly recommend that you do that once at home. There's nothing particularly deep in it, but you just need to do it. And if you don't do it, you will probably not be able to make much sense out of this equation. But it's just tedious, and I think this is best done in the privacy of your room, and you lock yourself in the room and you walk out when you're done. So let's actually try to understand what's going on, because that's more fun. So kt prime, let's say kt prime t prime, this was the variance for this variable t prime. And what I'm seeing is that t prime given t is given by a normal distribution with this mu tilde and k tilde. And so k tilde is given by, how uncertain t prime was in its own right. Right? However, this is now reduced by how strongly t prime and t are correlated. So basically, by knowing t, my uncertainty in t prime is reduced. And it's reduced by a lot if t and t prime are strongly correlated. Which is what it should be, right? If height and weight are perfectly correlated, then knowing the height pretty much allows me to read off the weight and vice versa. Okay. So if there's strong correlation, that's useful. However, if t itself is also a very uncertain variable, then that doesn't help me very much. So that's why I end up dividing by ktt. So if the variance in t is huge, then that to some extent mitigates the correlation between t and t prime. The other thing is, obviously this quantity here has to be positive semi-definite, so this can never become less than 0. Because we can't have negative variances. Right? So this thing is also called the Schur complement. Let me just write this out, the name. Okay. So this is the covariance. And so therefore, if I want to have a predictive uncertainty, I just take my default uncertainty and then reduce it by whatever I observed. It's useful. Now let's look at the mean. For the mean, basically what happens is we just predict that what's going to happen is what we would have expected to happen anyway. But we need to calibrate that by how much t deviated from its own mean. So if t deviated a lot, then okay, I'm going to get a lot of calibration. Now, that deviation, however, is tempered by how much of a covariance I have in t itself. So if t is very unreliable, I'm not going to heed much this deviation. On the other hand, if it's strongly correlated with t prime, then of course this should tell me something. So you have those two effects counterbalancing each other. So observing something extra will help you in this case very nicely linearly update your prediction. And that's it. And so now, if you look at that, this is basically linear regression, right? So we are essentially just using, those values t. And then we're using them just in a linear form to update our predictions on mu tilde. So it's linear in the observations, not linear in the covariance. So it's, say, linear in the y's, not in the x's. Okay, this is probably one of the scariest slides. I hope that it wasn't too scary. Any questions so far? Okay, so here's a short summary of this. So we have a normal distribution. We can sample from it. We can get mean and variance. And then the conditional is a Gaussian too. So now we can actually put this to good use. Would you please stop the camera for a moment and then restart it?